Yeah, how's it going everyone? Small here. So in this video we're going to talk about why your actual AI agent systems are failing in prod and how you can actually fix them with no bullshit at all and straight to talk without no theories here. But before that, let me just give you a little background about myself. So I'm the founder of Operating Systems and the principal engineer there. And I spent the last decade building mission critical systems across industries, and over the last stretch of my career, I've built and even got called into in to fix enough AI powered systems to see the same thing happens over and over again. We're talking about the same failure, but just different company, different stack, or even different industry every time, but always the same error. So that's why I'm recording this one, because there's a story everybody tells about why these systems fails, and most of the times it's actually wrong. And if you right now you're building AI agent powered systems, or you're paying a team to build them, or even if you already have one but it's not behaving the way that you want it to behave, basically believe in the wrong story that would cost you a lot of lost months and resources. So in this video I'm gonna walk you exactly through what actually breaks with no theories, and this one is actually from inside many real systems. So just give me 20 to maybe 35 to 40 minutes, and yeah, after this one you're gonna understand exactly how you're gonna fix your system and get it to where you want it to be. So let's go. So first thing I want to get to do here is actually get you out of the code entirely. So forget the code base, forget AI, forget all of that just for a second. Because if you stay in the code, you just keep looking at the wrong place there. So for this one, let's say we're going to an airport. Just stay with me for a second, because this actually maps into your system perfectly, and I'll show you exactly how. So for this one, this is the actual plane here, right here. It's your model, the AI, the pilot. Basically, it's so skilled, it's capable, and also it's the expensive part, and also it's the part that everyone gets obsessed over it. And in reality, it's almost never the reason your flight will ever get delayed. So but actually, I want you here to think about the last time that you got stuck on runway. Maybe an hour, 2 hours, going nowhere and just waiting for your flight. So who do you get mad at that time? The pilot? Maybe the airline? Basically, or maybe even the person that you can see just right through your face. And for that, you may say it's the pilot fault, it's the airline fault. Just saying in other words, just saying the AI is bad. So the instinct actually feels right, but it's actually super wrong. The reason of that is because the pilot never touched the thing that delayed you here. Maybe your delay was born somewhere that you cannot even see. Let's say 3 states away, maybe inside an air traffic control. Maybe you're talking about the coordination layer. Basically, we're talking about the system that's tracking 1,000 planes and 1,000 hands off at once, and just that pilot of your plane just has zero control over any of it. So here's the entire talk in just one sentence here. I want you to hold onto this one, because everything I'm gonna show you for the next of this video, the rest of this video, is just proof of this, just one line. So what's happening is you're blaming the visible part of the failure that actually lives in the coordination. So for our case, the model is the equivalent of the pilot here. And the teams that I see swapping models for maybe weeks, all they've been doing is just they're swapping out perfectly good pilot while the control tower is on fire, for example. So what's end up happening is they'll be fixing the one thing that was never broken in the first place. Now let me prove exactly to you this what's always going to happen no matter what. So this is the part that nobody sits down and does the math on it. And once you see it, you cannot unsee it anymore. So let's say like each step of your agent works 95% of the time. That means like 19 out of 20. And now like you hear 95% and your brain files it under this system is actually reliable. Maybe like say even like say this that's a good grade, that's an A plus, and you chip that system right away, for sure. But I want you here to watch what actually happens when you connect the steps together. So step one is 95%. Step two, still each one 95%. 3, 4, 5. Okay, now for these are like 5 steps. Each one would have 95% reliable. So the whole thing is 95% reliable, right? And that's actually the intuition and that what everyone would assume here. But the actual reality for the system, it would be only like 77% reliable for this case. So 77%. Just we're not talking about like not one of these steps was below 95%. So, and every one of them got like passed its own test, and in the end they just got chained together. And now after that they just deliver 77%. You may find this a little bit weird. And here's the thing here. So, and this thing I need you to understand it very well, because like this is the whole game here. Basically, the reliability that you lost here, it didn't just live in any one of these steps here. Basically, you can go and audit every single step here, and every one of these would show you that they're actually fine. What happens is actually it lived in the connections between them, and the wiring of each of these steps. And that's actually why most of teams can find this issue here. So what they end up doing is they profile the model, they test each component, and everything would comes back green here. And although that the system is still broken. So the reason of this is because they're looking at the parts, and the reason of this failure is actually happening not inside the parts, but when combining the parts together, and exactly in the space between each of the parts that we're connecting together. So basically multiplication is brutal, and like almost nobody in this space is doing the multiplication as they should be doing in the first place. And here's the part that makes it even worse here. This would get super ugly the longer that your task would run on this system. So same agent with like the same 92% per step this time. This curve isn't actually super complicated here. It's just like what happens to your success rate as the tasks gets longer and longer. And as you add more steps, that's what ends up happening. Now, 3 steps here. That's the demo. 78%. Looks incredible in a pitch meeting. Everybody claps. Now 8 steps. A small real job maybe, and now you're at the coin flip type of reliability. Basically, it's this system is useless now. And now let's say 20 steps, and which is actually like an actual production system would have even more than 20 steps. And at this step, and right now it's failing more than 90% of the time. Almost like it's failing more than 80% of the time, I bet. But now let's make it even more, what happens in actual production system. Let's say 40 steps in this system, and at that stage the reliability of the system drops to only 4%, which means the system is unreliable 94% of the time, which means that 10 times of let's say how many, let's say for example 6 times of 10, so more than 6 times, I mean, do the math here. 96% 96 times out of 100 it will fail, and just succeed on only 4 times, something like that. So basically it never get finished, and the systems is way worse than just flipping a coin flip at that time in production systems. Now look at what changed across like the whole curve here. Not what happened here is not the model. The model stayed the same, and not even the prompt, because the prompt didn't change here. The only variable that changed here and is how long the task was and how many steps it took. That's it. So when somebody tells you the demo was mind-blowing but production is garbage, here's what actually happened in this situation. So the demo was never lying in the first place about the model itself, because the model's always the same. The demo, what happened actually is that the demo was lying to you about how short it was, because it showed you 3 steps and just like let you assume 40 would just work the same way at the 3 steps. And when it comes to 40, that's a completely different universe here. So that gap between the demo and production isn't actually a quality problem here. It's this curve and it's math here. So now let me flip the question around, because this is the number that should generally scare you at this time. So what you want to do is you want to build a real agent, let's say 20 steps or even more, and you want it to actually work in production, not just like in like 3 simple steps in a demo. You want actual system, reliable system in production. So let's say 95% of the time reliability end to end. That's super reasonable ask to do. So what does each individual step need to hit for in order for this type of metrics to happen? It needs to hit 99.7%. We're not talking about 95, because that's not even close here. 99.7. That's like 997 times out of 1,000. Every step, no exceptions at all. And here's why this matters so much, and even like more than you think at this moment, because 95% per step feels like a lot. It feels like you're basically like there, and you just like need maybe to tighten it just a little bit. But in reality, you're not even there. You're so far away, like you're many galaxies away. Basically, you're just off by almost 2 orders of magnitude on the error rate. That's it. You're so close to failure than to success at that time. So what I mean is like near perfect when it comes to production systems, especially for this type of systems, is not the same as good. They're not neighbors at all. Near perfect is the same as failure in this type of systems. And getting from one to the other is the real engineering where it's happening, because pushing just an agent to 95%, that's so simple, but pushing it from 95 to 99.7%, that's real engineering here, and it's not about prompt tweaking at all. So the answer isn't about a better model or better prompts. And so now what I'm gonna do is I'm going to prove to you in just a minute that is flat out isn't than what it actually is. So the answer is understanding how these two things actually break. And after me doing this across a lot of systems so far, I'm building a lot of pattern recognitions. What I can tell you here is that there are exactly 5 ways. So let's go through each of them one at a time, because this is where it stops being theory here and starts being actually real here. And this is where the most value of this video would be reside. So as I told you, like 5 ways where it can break, and you already met the first one so far. So the first issue is they multiply. We're talking about small errors compound across steps, and that's the 77% I just like walk you through. 2 is they inherit. So let's say one early error becomes the foundation of the next one, and the next one. So basically that every layer after the error happens, just will build on the error and just keep going. Third one is they can't be undone because because an agent for an AI agent doesn't just like talk. He actually acts and executes certain tasks, and some actions can be undone, and some cannot be undone. Some cannot be taken back. Fourth thing is they can be seen. So the failure is completely invisible while it's happening. And fifth thing is they chase the wrong goal here. So basically, like the thing that they optimize exactly what. Basically, what happens is like they would optimize exactly what accidentally you told it to, which is never quite what you actually meant for it to happen, or what the expected output that you want from this AI agent systems. So now every single one of these is actually like a real system I got pulled into. These aren't hypothetical situations here that I just like made up for a slide. So let me walk you through each one of these with the actual numbers, because numbers are what makes these more real. So let's start with the first one. For this one, it's actually like a real system, real company, and the very step is the Shane missed just like one document, just one. That's it, no more than that. And like that's the whole seed of this whole disaster that happened to them. So just like that one wrong assumption, what ended up happening is just got handled into the planning step, and then planning took it and just like generated three substacks out of it, and each of these three just inherited the original mistake, and their outputs become the input for the next step and the next, etc. So basically, like five steps down the chain, the output had nothing to do with reality anymore. It was confident, but at the same time, it was completely wrong here. And here's the part that generally messes with people when I actually explain it here. So every single step, basically like every single step in that chain was flawless. The model did exactly what we asked it to do. But what happened is it reasoned perfectly, like from the beginning until the end. But the issue is like just like from a starting point, it was already poisoned. So that's the whole reason for this. And you know, like the old line here, garbage in, garbage out, and this is worse than this is garbage in, and then the garbage compounds, and every step downstream treats the garbage as settled facts and just like keeps building on it. And what ends up happening is like nobody goes back and check the source, so the error doesn't get caught at all, and just gets buried deeper with every single step. Now, here's what we actually did in this specific system, and I want you to pay like great attention here, because this is like the pattern for the whole talk here. What we did is we did not touch the model at all. We just like rebuilt the system so that every step could reject bad input instead of just like blindly accepting it and swallowing it and moving to the next one. And that way we eliminated the cascading failure, and just by doing that the whole cascading failure dropped 82%. So for this fix, it was the same model, the same prompts. What was different is just like a different system, and like an 82% increase. That's it. Oh yeah. Now let's move to the next one. Now let me show you exactly why this actually happened. So at least for this one, I'm gonna show it to you how it's actually happened at the mechanical level, not so. And this is like the one picture that I really want you to keep in your head moving forward, because it will explain almost everything for you. So this is what your agent will actually see is here. This screen. It's the story the agent has built up for itself so far, step by step. This is its entire reality. This is in this entire world. He was born and died believing this is his world, nothing more than this. This and like this green dot is where the agents think the plane is actually is, and what he actually believes is to be true here. And this dashed one, like just over here, is the actual reality, the actual what's going on, where the plane actually resides, and where the ground truth actually be. Now, watch when these two drift apart and nothing in the system checks the gap between them. What ends up happening is the agent would keeps navigating by the green dot, by the screen that they have, and every decision that would make it from the moment on is to be made like against reality that's already stopped existing so far. And here's what I need you to make from this simple visualization here. So this is not like the model being stupid at all. The model is actually reading its screen perfectly. The model is reading it's doing exactly what it should. The screen is just like wrong at the beginning, and nothing in the system told it the screen was wrong, and that's what happened. And basically the map has changed, but the agent has no way to know that the map changed. So in order to fix the gap, and basically like just by fixing this gap, you would fix the whole failure here. And fixing the gap is actually systems work here, and not model change. It's not about changing the model or even about changing the prompt, because it has nothing to do with that. And now here's where why nobody would catch this in time, and this actually the cool part here. So basically this is the correct step here. It's confident, it's clean, it's got citation, and basically it looks right. And this one is wrong step. Looks at it, it's identical, same confidence, same clean formatting, same citation. So the thing is like wrong answer would wear the exact same uniform as the right one, and here's the actual mechanism underneath that. So without I'm not actually sure about this, that what gets destroyed the instant the step is written down. So what ends up happening is like, for example, the model might have been 51% sure, or maybe like 99% sure, and just on the page it will just like look exactly the same one as 51 as 99.99% sure. It will behave the same way, and basically that uncertainty would would be the whole reason of this whole issue, because it will just carry on, and the model would act on that uncertainty here. So the one thing that you're counting on to catch mistake, like that little instinct that goes behind that, and just say, and like what you want the model to do is just say like, oh wait, that looks off. It will never get fired at all. So because like nothing looks off at the beginning, and everything looks good. So that's what makes this actually super dangerous here. It's not wrong in a way that looks wrong. It's wrong while exactly like right, if you understand what I mean. So now here's what makes agent genuinely dangerous, and not just annoying here. And actually this is the line that separates chatbot from an actual agent here. So for chatbot, it just like writes words. If it's wrong, then you just like read it. You go like, this is wrong, you delete it, and no harm be done. And the cost of this mistake is basically almost zero, as long as you didn't act on the wrong information. For an agent, it's way different, because an agent would act. What happens, for example, an agent can send email, charge the actual card, it deletes the actual record, plays the actual order, and those actions only turn one way. Once like step takes an action, you cannot take back that action again. And just based on that poisoned starting point we just talked about earlier, nothing downstream can undo that mistake. So because it's already happened, and basically it's gonna be happening at machine speed, and it would be way faster than you could even like reach in and just like hit stop before catastrophic happening. So that's the downstream cascade that doesn't just like end in a wrong answer sitting in a log, but just like leaves like a real trail of real irreversible damages in the real world. And let me show you what that actually costs when it actually goes wrong here. Let me drink some water. So, $440 million. This is actually the night capital. We're talking about 2012 incident, where for this one, like an automated trading system they built, and what happened is for the system, they pushed a bad deployment, and there like was no working kill switch at all in that system, and because of that, the system lost $440 million in just like about 5 minutes. That's crazy, and that's effectively how like a whole company ended up being around for years just for this small mistake. And I want you to hold this framing carefully, because it's the whole thesis in just like one event. The code was the last domino effect. The failure was the system that let it run in the first place with no breaks at all. So the code did what the code does, just executed it, and the system had no way to catch it up or stop it. And if you understand this, this is not a code problem, it's actually a systems problem here, because the code was just like the last domino in in the whole place here. So I want you to remember that one. Now, for wave 4, honestly, this one is that's keep happening most like, and based on what I've seen, most of you just like get stuck here whether like you realize it or not. So this real system had 11 distinct steps happening inside it. Let's say 11 internal stages of reasoning and action. And let's say it logged exactly one thing here. Like, did the whole thing work? Yes or no? Maybe one bit, or everything in between. All 11 steps would be like completely dark with no visibility at all what happened inside these. So what happens is like when it failed, it would just like look random, and this is like a phrase I just keep hearing it again and again and again. I'm just like tired of it. Even like from good teams, I'm not like saying they're bad people. They're actually good teams and very reliable. But most of the times, many of these teams will just like keep saying, just failed randomly. We cannot reproduce this issue, and I'll tell you exactly what I actually tell them in that situation, because there's no such thing as random failure. There's only failure that you can't see, and the randomness that you're talking about isn't in the system. It's your instrumentation. So what that means is actually you're blind, so just like looks like chaos for you. So on the system we did like the obvious thing that nobody had done. We just like turned the lights on, and we instrumented every single step. And what ends up happening is like 85% of the failures were coming from just like one step, and just like one specific step out of all the 11 steps. And Like it took us 2 days to find, and once we could actually see it, it only like took us 2 days after that for the team to fix it. And the moral of the story, it was never like a reliable system. It was just like one broken piece of the whole system, just like hide in plain sight because nobody was watching like in the middle of what's actually going on before the agent was producing their output. Like the second we could see that, the mystery just evaporated and stopped from being random failure to actually finding what actually caused that failure. So that's the power of visibility. You cannot fix what you can see, and almost nobody can see their own agents. So that's the thing that you need to be aware of. And look here. So if you think this is some like new AI problem, it's not. These things are actually so old. I just like want to zoom out for a second so you can actually see the pattern is way bigger than AI agents or AI at all here. So for this one, let's say this situation is like 50 million people lost power in the northeast in 2003, and part of the reason it got as bad as the did was basically like software bug that quietly stalled the alarm system in the control room. So what happened is like the operators were sitting there flying blind while what ended up happening is the grid was cascading and failing all around them without them even seeing what's going on. So for this one, it was not the failure itself that did the damage. What did the actual damage there was the view of the failure went dark. So the operators trusted the quiet because quiet is supposed to mean everything's fine, and in that situation it was not. So that's like the same exact disease as your agent. So the system just kept running while just small failure compounds, and nobody could ever seen it, and just like much bigger blast rate. This example just like have much bigger blast rates. That's it, but the same thing, same pattern. And this isn't just like me and my war stories here. And in case that's your thinking, this is just like one guy's opinion here. So basically, like researchers went and actually studied how these multi-agent systems fail across hundreds of your execution traces, and they categorized them like they categorized every failure, and here's what they actually found here. So about like 40% of failures, the reason of them is because bad specification and design. So what that means is like how the system and the rules were defined in the first place. Second thing is about 37% of the cases was about coordination between the parts, the handoffs, and exactly what that means is exactly like what we've been talking about earlier. Third thing is about 21% of cases it was because like nobody checked the work. There was no verification at all. And those up like specification, coordination, verification. That's essentially all of it. That's the whole pie here. And here's the punchline that ties this entire talk together here. None of it is the model fault. The study went looking, and the failure were in the design itself, the coordination, and the check-in. It was never about the intelligence. So my war stories here are not like some random exceptions here to this specific research. They are specifically this research playing out in the field. With also like the dollar figures around these failures dashed. So now let's go back and just like we need to reflect from the beginning here. So your system's failing, so you would reach for a better model, bigger, newer, smarter, and feels like the responsible and most obvious move here. So that's the trap, and let me show you exactly why. So here's what everyone does. They swap the model out and you just keep the loop open, reason, act, reason, act, on and on and on. And nothing anywhere in that loop ever gets checked, and so we don't even know if the last step actually was right or not. And it just like trusts itself and just keeps going until it fails super bad. And here's actually like the part that actually matters here, because the part that makes just use a better model not just like useless tip, or for many like, unfortunately many like technical experts, or at least they name themselves technical experts, but it's actually way worse than just like useless. It's actually actively worse and is doing more harm to people than good. Because like smarter model would just would be if it's been dropped into the same open loop, it was just like reason more convincingly from the same wrong starting point. So what ends up happening, you will not get fewer failures, you just like get more articulate, more confident, more expensive failures, and basically like the mistake just would get better dressing, that's it. So what ends up happening is, so basically if you're doing that is it's like you're treating the patient before you've run the whole scan. If it was a doctor doing that, it would be a malpractice, and unfortunately many technical people do that, and it feels like progress the whole time you're doing it. But the actual fix was way bigger, but like it was never like a bigger brain or more skills here. The fix is just like check between the steps and just like close the loops more effectively. That's it. So here's like what actually works, and this is the part that you can go to do something with here. And I want you to notice one thing about this entire list. So one, see it, record like every single step, so that when something breaks, the broken step is actually findable, not just like a mystery, it should be findable. Two, you need to check it, so you need to verify like step before the next step is allowed to trust it, and you need to close the loop. Next thing, you need to structure it, like you need to let the step project a bad handoff instead of just like swallowing it whole without any verifications. And just like that's like the 82% fix. 4, you need to contain it. So what you need to do is like you need to stop a failure at like its source before it spreads through the whole chain forward. 5, you need to bound it. So what you need to do is like you need to limit what the thing can actually do on its own, and you may, if the agents are doing some very critical tasks and what's end up happening cannot be undone, then you need to put like a human in the loop. If anything if any error can happen, the human can pull off the switch and kill the system right away, or at least stop it, so it will not cause more harm. Now I want you like to look back at the whole list here, not like one single item on 3 is use better model. Like every one of them is the system around the actual AI model and the AI agents. We're talking about the orchestration, the verification, the state, the guardrails, and here's the generally like good news buried in all of that. And it's the most important thing that I would say today in this video, because this is actually buildable right now, and you're not like waiting on OpenAI or Anthropic or to ship you like a better model or maybe new framework for better AI agent orchestration or stuff like that. You're not waiting for anyone. The fix is just like engineering here, and this engineering you can start today, right now, and you can fix your whole system, or you can build it right away now if you didn't build it yet. And basically, like, I know this works because I've done it multiple times, and this isn't theory. So 82% fewer cascading failures, which is like the number from that first war story. So it was like the same model, same prompts. We just like engineered the system properly around it, and that number, that like 82%, is actually here as architecture. It was never intelligence, and that's like the entire point of everything that I've shown you so far. The leverage was never in the model. It was never in the tech itself. It was always in the system and the engineer on how you orchestrate everything together, and all the other points that I've told you in this one, in this slide. Okay. Now, now here's like where this actually gets way bigger than AI agents, and bigger than machine learning, and bigger than AI, because this pattern I've like been showing you so far, it was actually never about AI in the first place. So the model is actually like just like 5% of the whole thing, like that little box at the very top. Then we have pipelines, 95%, protocols, 95%, drivers, firmware, silicon, the actual metal here. Basically, like all of that, like everything under the model, that's like the 95%, and that's like 95% is where the failure actually lives. And everything, and that's like what's happening is like in every single one of these systems, because the model was always just a small part, just a tipping point. It was just like it will not do any difference if you change it, basically. You're just like wasting your time and money. And here's the thing that most people completely miss here. This exact pattern, just like one small error would compound through a whole system that nobody's watching. It will shows up in systems with not even like AI models in them in the first place. For example, let's say like a fleet of 25,000 servers. They would all like need to talk to each other over hardware protocols, telemetry pipeline moving data off physical machines, protocol integration reaching all the way down to the silicon. Basically, all these problems have like zero AI in it, like anywhere in the system, and the exact same disease kept happening even there, because this disease was never about AI in the first place. It was about production systems and the space between each part of this of each specific system. So this is where I actually work, and it's why I see the stuff that other people miss. So model to metal, like the whole stack, that's what I've been doing, top to bottom, and across the entire life of system, not just like one slice of it, and across multiple industries. So what we do is like we diagnose it, architecture it, build it, harden it, and operate it. And here's like why that range matters a lot practically, because like most firms just like live in just like one single layer, maybe architecture, building, something like that. So what they do is like they know just like the model, or that's they would know just like the infrastructure, or they would know just like the pipeline, but just one, and just one. So, but the failure actually I've shown you before, over and over today, almost always lives in a layer that never even thought to open with. So they can just so what ends up happening is most firms can't even like find the actual error and fix it. So they would just like address it and add some things that may make the system works for small period of time, but that's not actual permanent fix. So yeah, this is like the actual mechanical reason you can find you can find what everyone else walks right past this issue. So here's what I want you to walk away with from this video here. If you ever like forgot anything we talked about so far, so basically like your model is probably fine and That's like 99% of the times. The failure was almost never in the smart part. It was always in the system around it, the coordination, the handoffs, the verification. Basically, the parts that nobody's watching and nobody's is actually instrumented. So the model is just like the pilot. The failure was always in the airspace, not the pilot itself. So if like yeah, so let me do this. So basically, like if you got a system that demos beautifully and then just like falls apart the second it hits reproduction, or maybe you're thinking about building a new system, either AI powered system or even like not AI powered at all systems, and you want more help. I just like wanted to hear this clearly. This is not like a model problem. It's just like it's not even like Q problem either. It's just like systems problem, and it's a solvable one. And basically that's the kind that the kind of things that I've been doing for the last decade. If that's you, and if you want more help, more specialized help, if you have like any specific problem that you're facing right now, either with building or with already existing system, just hit me on my email and I'll write you a more personalized reply on your exact case. Just like with zero commitment from your side, I'm not telling you anything right now. And if you want to partner together, you can always like send us email through the form, our website, and we can see how we can arrange a partnership where we can help you, because we only work with few clients per quarter. So that's the whole thing. That's the whole video. I hope you like it, and if it was helpful, just leave a good comment and just subscribe to the channel. So take care. Bye.